So let's go about A62 relative velocity. Today we're going to use maybe the water current as an example of. Sorry, I'm with this scarf. I am a little under the weather. We're going to use the water current as an example to help you understand what is relative velocity. When one velocity affects the other velocity, that's the relative velocity. For example, when the water current really affects the rate of your own velocity. Maybe let's use a kayak as an example. So let's say, let's start with the upstream and downstream. So upstream, so there is a waterfall creates upstream or downstream depending on which direction you're moving with your kayak. So you have a small kayak, you're paddling, right? If you move this way, and then of course this is downstream. Why this is downstream? Because you are moving at the direction of the current. Let's say the water velocity of water is 3 miles per hour, and you're moving this direction, meaning that the downstream, you get the support from water current. What would be the upstream? Would be you return to location A from location B. That would be the downstream. All right. What causes the downstream or upstream? Waterfalls. If you remove waterfalls, there will be no current on the water. If there is no current on the water, then that would not be a relative velocity problem. So you see that two velocity here. One velocity you paddling the kayak. You paddling the kayak. So you paddling the kayak. So I wanted to find you paddling the kayak. That's what I want you to find. Let's say the time it takes, right? So it takes from here to here so you start location A, right? Location A, let's say location A is this one. All right, from here to here is 2 miles. So you move 2 mile, okay? And it takes same amount of time to move half a mile, right? So this is location A to location B, all right, and B to location C, all right. Takes same amount of time, right? What does that mean? This is half a mile, so half a mile. So it takes same amount of time because the downstream it takes t is equal to at time t you can move 2 miles at the same amount of time you're spending. Upstream you can move only half a mile because you're moving against the current. You see, I want you to find the velocity of your paddle, right? So how can you find it? All right, let's see. So let's say velocity. Well, let's start with this conversation. Velocity is or let's say distance. Distance is VIT plus AT squared. And let's say acceleration, there is no acceleration. So the time would be the same. So time is d over v. So you have a d over v, okay, for you're going to say upstream is equal to upstream, or maybe you want to say downstream is equal to upstream. Alright, so downstream, let's say d over v is equal to upstream d over b, because it takes the same amount of time. Maybe you want to write t is equal to t. Alright, t is equal to t, that would be more accurate. Alright, half a mile, more accurate. But if you write d over v is equal to d over v, that's not gonna be right, right? Because in this case, UD is, of course, the downstream, UD is 2 mile. So you want to report that 2 mile. In this case, UD is not 2 mile. UD is a half a mile. You want to report that half a mile. Why is the reason? In this case, the velocity, whatever the velocity is, let's say that your pedaling velocity plus, this is plus because you get the support from the water, plus 3, and this one your pedaling velocity minus 3. You don't get the support because you are moving against the water. Okay, so you do cross multiplication. So 2v minus 3 and a half v plus 3. If you do that, then you have over here 2v minus 6 is equal to what? 2v minus 6 is equal to half v plus 3 over 2. Now you multiply both sides by 2. Alright, so what are you going to get? You're going to get 4v minus 12 is equal to 2 to cancel, you have v plus 3, right? So you 4v minus v would be 3v is equal to 12 plus 3 is of course 15. Velocity is, now as you see, 5. So your paddling is, how fast you're paddling? 5 miles per hour. Alright, let's see whether that is right or wrong. So if that is right, then this one has to be equal to this one. So this is 2, b plus 3 is equal to half v minus 3. So 2 over 8, and this is 0.5 over how much? 2. And then this is 1 over 4, and this is 5 over 20. And they are the same. Okay. So you understand the relative velocity. So we're going to make this problem a little different now. Probably going to keep the same idea. Alright, I'm going to keep the same idea. Okay, the waterfalls is still here, waterfalls. Okay, so Mr. Barry is over here and there is a river, and Mr. Barry this time he just he doesn't have kayak anymore. No more kayak, he just want to swim from here to here, right? And the distance from here to here is 100 meters, and this is a river. This is a river. This is a river, and this is of course downstream, and this is upstream. Downstream, so I have to put the arrow. Okay. All right. Downstream, there are waterfalls pull him to the center of the water, and the distance from here to here is 50 meters. Of course, I didn't draw it to the scale. Mr. Barley can swim 1 meter per second. All right, 1 meter per second. So that's his velocity. I'm gonna find the time for him to get from here to here, right? From A to B. So the time is, again, distance is VIT plus half AT squared. So there is no acceleration. So time is distance over velocity. So T is distance is 100 meter and velocity is 1 meter per second. Meter cancel. So you have time is 100 seconds. So it takes him 100 seconds. Right? To go from location A to B. Now we also want to find the current of the water has to be so that he survive. So this is 50 meter, right? Okay, so what would be the minimum current of the water be so that the man survive? Okay, all right, so how can we find it? We want to find the velocity of the water. Velocity of the water is, again, d over t. Now d is in this case 50, so velocity of the water 50, and then the time is of course 100. So that velocity of the water is 0.5 meter per second. Meter per second, all right, 0.5 meter per second. What does that mean? If the velocity of the current is 0.5 meter per second or less, then he survived. What does that mean? Why? Because hey, d is VIT. So if V is 0.5 and T is 100, then this is 50. So from him to the waterfalls is 50 meter, right? If the current is a little bigger, say 0.6 times 100, that would be 60, and 60 is inside the fall, right? Waterfall. 50 is not inside the fall. So that means 0.5 is the minimum velocity of the water which will allow him to survive. If the water velocity is a little bit more than 0.5, say 0.51, then he will die because he will be inside the waterfalls. It doesn't matter whether at here or here, you die. So that's the scenario. Okay, good. So here, this is his velocity. Now, what would be, that would be the water velocity. What would be his velocity? Okay, so let's see. Let's use the different color. So now, if you go this direction, right, with how much? 1 meter per second. And the velocity of the water is 0.5 meter per second. Then what would be the total velocity? The total velocity would be square root of 1 square plus 0.5 square, and that is B total would be 1.1, right? Okay. The 1.1 will not allow him to survive, right? No. So what did he do? He changed his strategy. So how did he change his strategy? So he come over here, and instead of moving to perpendicular with the direction of the ground, he changed the strategy. He moves to the angle, all right? And again, his velocity is 1 meter per second, and let's say the current, the true current of the water is 0.8 meter per second. Now the total velocity would be, now what would that be? C square is equal to A square plus B square. Now of course C square is equal to C square minus A square is equal to B square, and this is the B, right? So C square is 1 square minus 0.8 square is equal to B square, and B turned out to be 0.6 of course meter per second. So this is up down, this is up down. So how long it's going to take? So T is equal to, if distance is V, T is equal to D over V. The D is still 100 and this is 0.6, so this is 167 second, and that's how long is going to take for him to go from location A to location B. All right, we're gonna be talking more about it in the classroom.